Project 2.4.3, ISP.Medium, the transistor-based binary counting circuit.
For this ISP.Medium, I designed and built a transistor-based binary counting circuit. The purpose of this project was to take the idea of a normal digital counter and unpack it down to the transistor level so the internal logic could be understood. Here is the full transistor-based binary counter.
This circuit counts using sequential T-latches, where each latch stores one binary bit.
As the clock signal oscillates, each stage changes its state in sequence, allowing the circuit to count in binary from 0 to 9.
This circuit is built from transistor logic gates. The gates I used were NAND, NOT, and AND gates. The NAND gate works by the output being high, normally when VCC flows through the 10K resistor and out the output. However, when both inputs A and B are high, it causes the voltage to short to ground, which causes the output to go low, meaning the output is only low when both A and B are high. The NOT gate works in the same way except with one output. So VCC normally flows straight out of the output unless A is high, in which case the voltage will be shorted to ground and the output will go low. The original AND gate design works by putting the output on the other side of the two inputs transistors, meaning that current should only flow when both A and B are high. However, because of transistor leakage from the base pin to the emitter, if only B was high, there would still be some voltage flowing out the output, giving us a high when there shouldn't be one. So our workaround is to combine the NAND and NOT gate to take a successfully working NAND gate and then just invert the output, meaning that when both A and B are high, that's the only possible way to get a low out of the NAND gate, which is then the only way to get a high out of the NOT gate, which forms an AND gate. In this Fallstad simulation, each bit represents a T-latch from transistor-level NAND gates in a master-slave configuration. The latch toggles on each clock cycle because its output is fed back through the logic, so the next state is always the inverse of the current one. You can see the first latch switching through every pulse, while each subsequent latch toggles at half the frequency. This is because its toggle latch is only high when all previous outputs are high, creating a sequential counter. This will reset at 10 or in binary 1010 because it will trigger a combinational logic that will set the reset line to low, causing every T-latch to go back to 0.
And here's my prototype I built off the Fallstad simulation. It featured the oscillator, the reset line, which is this array of red wires, the output, each 4 bits, the combinational logic for reset, and the sequential logic.
Next, I will show the preset function in Fallstad on one T-latch. This preset I designed allows a bit value to be preset on the counter. It works by shorting the reset line and using a switch to internally set both inputs on the SR NAND latch to the chosen value.
The preset function along with the reset pin are present on the final device, however unfortunately didn't function as intended. It is also worth mentioning that my discrete A-stable multivibrator design seems to be messed up, so I had to replace the clock signal with an A-stable 555, which works because of a timing capacitor continuously charging and discharging between the internal 1/3 VCC and 2/3 VCC thresholds, causing the output to switch high and low in a repeating cycle. This configuration produced a steady square wave clock signal needed for my project.
Finally, I will show a clip of the combined transistor-based counting circuit. The design cases feature mechanical interface, allowing the two cases to be attached using locking poles. This final version brings the separate projects together and demonstrates the overall goal of the project, creating a functioning counting circuit at the transistor level.